People have reported anomalies since the beginning of recorded history. Lights in the sky, strange glowing phenomena, and the like. Now, you might assume that in the scientific age, these reports would go down in number, that we would essentially explain them away. Yet the opposite seems to be true. The recorded accounts have increased, the evidence has gotten stronger, and scientists are starting to take these phenomena seriously. Dr. Kevin Knuth is one of those scientists. In the description, you can find his professional background as well as the publications referenced in this video. I honestly could not have asked for a more intelligent, interesting, and gracious first guest for this channel. We discuss a lot and get into his work on the foundations of physics and how he sees space-time as something that may emerge from deeper relations. I wonder whether that framework could be related to the unexplained things people encounter. Be sure to let me know what you think about what we discuss. And if you enjoy exploring science at the edge and beyond, I hope you'll consider becoming a part of the community here. And if you want to catch future episodes, be sure to turn on your notifications. Let's get into it. Real honor speaking with you today. You bring something that is rare in modern science. Deep work on the foundations of physics alongside a careful willingness to engage in data that sits at the edge of our current understanding. I first encountered your work through a talk where you discussed how many ideas we now regard as foundational were once strongly resisted. You discussed examples ranging from atomic theory to germ theory to geophysical phenomena like earthquake lights. Those historical examples have always inspired me along my way, especially as I was preparing this channel because I hope to explore science at its edges. Could you walk us through a couple of examples that you think best illustrate this pattern and why they remind us the importance to stay open to the data regardless of where it takes us?
Oh, yeah. It always, amazed me at how difficult it was for some of the new ideas to be accepted. And especially when I started working to study UAP and saw the huge amount of resistance there to even considering this as a reasonable thing. And especially when you sit down and think about it, well, it's not entirely unreasonable because, especially the extraterrestrial hypothesis, because we ourselves are trying to do that right now. And so to assume that nobody else would is a very strange way of thinking. And then the idea to think that it's incredibly expensive. No civilization would try to do it. Well, we don't do it because we're going to war all the time. We spend all our money on war machines and fight each other. If you've got a civilization that doesn't do that, they've got all this effort that they can expend to explore. And so I, in trying to explain to other scientists why new ideas shouldn't be surprising, I started looking more closely into past ideas to see how easily they were accepted, and several of them were really contentious. The continental drift, those debates went on for 150 years, 150 years for them to settle this, and in part due to the fact that in the beginning, there was no good explanation as to how continents could move. They didn't have a good theory of what was going on under the Earth's crust to be able to explain that. And so, despite the fact that almost every kid, when they pick up a globe at age 4 or 5, recognizes that South America fits into into Africa, it's obvious to a child. It's not obvious to a scientist, right? And part of that is there was a lack of a foundational understanding of how tectonics could work. And I think so this is one connection to my work on foundations of physics. And it's hard to know that in the late 1800s, it was believed that we pretty much understood everything. And in fact, Lord Kelvin is renowned for making several statements to that effect, and 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 opposing some new ideas. X-rays will prove to be a hoax. You can never have a heavier than air flying machine, things like this. And yeah, I would love to take Lord Kelvin on a ride on a 747 for 7 machine. And I was actually in a podcast the other day, and I was talking to Luciano Volpe, and I said, I flew back from Austin last week, and we were boarding the plane outside and got to walk right up to the plane, which I love to do, and they are huge. I mean, a 747 is huge. It's a giant piece of metal, and even if you know the physics, it is really hard to get your head around how could Bernoulli's principle actually lift this thing up into the air. And that's hard to get your head around, but it works, and it does. And I think that that's what is not always appreciated, that some of these things are possible, although hard to imagine. And that's that simple. And so Lord Kelvin wasn't able to imagine heavier than air flying machine, despite the fact that he had seen birds, presumably throughout his life, and they are technically heavier than air flying machines. So for him to make such a statement's a little odd, but he wasn't referring to birds. He was referring to something that could carry people. His C-5 transport plane carries tanks. And I grew up in Wisconsin, I grew up in Fond du Lac, Wisconsin, just south of Oshkosh, Wisconsin, where they have the Experimental Aircraft Association fly-in every year. And so we used to go to the EAA fly-in pretty much every year and see all the new experimental airplanes, which was always great fun. And one year they had it was right after the Soviet Union was breaking up. They had an Antonov 128, I think the number is, bigger than a C-5. This thing is ginormous. They're gigantic. They were just shocking. And I'm straying off topic. You were interested in things like this, and so he didn't believe. Lord Kelvin didn't believe in X-rays, radio, and heavier than air flying machines, and even what is it? 2 weeks before Sputnik, the royal astronomer made some comment about space travel being bunk. And 2 weeks later, we launched the first satellite. So these things scientists are almost renowned for not being able to predict where science will take people. And I think that's because understanding how something works is different than using principles and concepts to design something new. That's engineering, and engineering is not physics at all. And I think a lot of people don't appreciate that.
Do you think that that's going on today in modern physics? Can you identify any areas where instead of maybe shutting down the conversation on new ideas, we should take them more seriously?
Yeah, I think this goes on all the time in all sorts of areas of science. I'll just throw stuff out. I'll just throw stuff out there, and everybody, and half your viewers are just going to scoff, right? But it's not. When you look into it, when you take the time to look into it, it's not easily blown off. Most of these things. So UAPs, UFOs. In fact, some of our efforts were just published in the USA Today last Wednesday, and they actually called it UFOs. They didn't go back. They didn't use the friendly massage term UAP. They actually went back to the old one with all of the all of the bad connotations. They went back to using UFOs, which I thought was interesting, and I welcome that because some of these things are unidentified flying objects, and they do appear. Some of them appear to be technologically developed craft. So that's certainly one topic. You have there are multiple witnesses I mean, this is rather common when people get close to UFOs. They also report really weird paranormal type behavior, either at the time or sometimes even afterwards, which is really bizarre. And that's, again, easy to blow off. There's claims now that some nonverbal autistic people are telepathic, and people have looked into this, have done some tests. I think we're not that some groups are now trying to position themselves to do actual scientific studies of this, which was interesting. Getting that through an IRB, I have absolutely no idea. I've had people ask me, I'm like, I don't know. I couldn't get my brain computer interface work through our IRB. I'm going to be allowed to test telepathy with kids. So that's so there's a difficult one, and so telepathy, remote viewing is another one, and that is interesting, and it's apparently used by the CIA has remote viewing groups, the DIA has remote viewing groups, and purportedly are successful to some degree. So, and I've talked with Hal Puthoff, who helped develop some of the protocols for that when he was at SRI, and he helped develop these protocols for the CIA to have their own remote viewing program. And he explains to me, he's a physicist, and explains to me this is not electromagnetic. We have done all the electrically shielded tests and magnetically shielded. And I'd asked him if he did those tests, and he said, well, I think we did better. We put the people in a submarine and we parked it on the bottom of the ocean. And I was like, and he says that it even worked. It worked better when they were shielded. So it's not electromagnetic. There's some evidence that it doesn't obey light travel time, which goes against some now very fundamental ideas of physics. So that's, again, also difficult. So those are some of the telekinesis and remote viewing. That's biology and physics kind of mashed together. Really weird thing. How real any of it is, I don't know. I've looked into it a bit myself sometime, to just see what's here. Is any of this reasonable? And it's physics-wise, it's really difficult to understand how you could have something like that.
Could you talk about how you got interested in science, the kind of problems that drew your attention early on, and what ultimately brought you to questioning the foundations of physics?
Right. Yeah. I mean, I've always been interested in how the universe works. That's really what drives me. I want to understand what's going on here. It's a weird place. And a lot of people tend, especially skeptics tend to think everything's normal and prosaic. No, there's nothing normal about what goes on in your daily life. None of this is normal. And it's all weird. So I've wanted to understand that. And that's really what drove my interest in physics. And I was always interested in foundational physics for that reason, interested in things like general relativity and quantum mechanics, try to understand what is space and time, and the quantum mechanics is a real mystery that is arguably still weirder than some of the things that people claim and are disbelieved. So that makes it a bit easier for physicists to deal with some of this stuff, I think, for that reason. We're used to dealing with phenomena that we can mathematically describe but not quite understand. And I think that, and I was always interested, and I got interested in foundational physics, especially. I think one of the main reasons is it's just simple and practical. I'm horrible at memorizing things. And my colleague Matthew Shadagas at the University at Albany, who we're both working on studying UAP together, and he has an eidetic memory. Mine really sucks. He remembers everything. I almost don't remember anything. So when it came to memorizing equations in physics, that was hard for me. And I had to to remember them, I had to learn how to derive them. So, and that's how I would remember the equation. Well, it comes from this, and then I'd have to remember the process, the thought process that leads to that equation, and then I can basically rederive it in my head, and then I have the equation, and that's basically how I survived in physics. So I think that's what that also contributed to my being interested in foundational physics.
For someone encountering your framework of emergent spacetime and information-based physics, how would you describe its core ideas and important takeaways?
Yeah, I guess I can maybe describe how that came about is maybe the better way to do it. Um, because my focus has shifted as that's progressed. So I first was interested in, I worked at NASA Ames Research Center in California before I worked at Albany, and I was in the Intelligent Systems Division. So we designed artificial intelligence algorithms before anybody knew that there was AI. So this was now, 25 years ago. So I was very interested in the foundations of probability theory, and I was interested in and in Boolean logic allows you to perform algebraic calculations that map to logical manipulations, right? With logical propositions. And I was interested in developing a calculus for questions so you could do computations with questions instead. So if you want to design a machine to do an experiment, you can think of an experiment as a question. And if you want to figure out what's the best question to ask or what's the best experiment to do, you want to calculate, the relevance of every possible experiment to the question that you actually want to answer. And that's what I was trying to do. So I was interested in the mathematics on how you might quantify questions. And that had me heavily involved with the derivations of probability theory and such. The best ones I found to be coming from applications of simple algebraic symmetries like associativity and distributivity. And that actually allowed me to develop a calculus of questions, which turns out to be related to entropy. Entropy is related to what you don't know, where probability is related to what you do know. And I was looking at some quantum mechanics, and it struck me that some of quantum mechanics, especially Feynman's path integral formulation, looks so much like probability theory. I mean, so much so that Feynman himself had written in a paper that perhaps it would be reasonable to think of negative probabilities, and he got there by thinking about complex numbers, quantifying quantum amplitudes. And I thought, I wonder if you could derive quantum mechanics this way, in the same way that we're deriving probability theory. And so I worked with Philip Goyal, who's a professor at Albany, and one of our other colleagues, John Skilling, who's a former professor at Cambridge. And we found that indeed you can derive the Feynman rules for manipulating quantum amplitudes, and derive the fact that they need to be complex numbers from assuming that you need two numbers, and that when you combine experiments in parallel, you have associativity. So it doesn't matter which way you put them together. And distributivity when you combine parallel experiments with in-series experiments. And that allows you just to derive all the mathematics for the Feynman rules for manipulating quantum amplitudes. And it just got me thinking more, well, how far can you push this? I mean, if you can just derive this, then what's going on? It's hard to imagine that you've got a supreme being, Mother Nature, who just declares laws of physics, right? And then you can derive some of them using some simple mathematics. It either implies that Mother Nature is incredibly consistent, or something else is going on. Maybe thinking of these as laws is maybe not the right picture. And so I was working with one of my graduate students, Nusha Bahraini, And we decided to let's see if we can let's see what happens if we strip down physics to a very simple model. And then we try to figure out what mathematics you could use to describe it consistently, right? And so we imagine you have a particle, and a particle can interact with another particle. And we're not going to worry about types of forces and anything like that. There's just an interaction. That's all you know. And the idea was that it's a directed and discrete interaction. We put those constraints in, and because it allowed us to quantify things with numbers. And so now you have a particle that then interacts with other particles and is interacted on, acted upon by other particles. And this gives you a graph of sorts and a partially ordered set, actually. And the question was, how could you possibly quantify this system mathematically? And we started playing around with it and found out that some of the algebraic symmetries constrain everything, so that it turned out there was only one way to do it. If the only thing you can really do for a particle is count events. That's the only thing you have is counting. And then for events, you can define coordinates based on when that event interacts or other observers along other paths are informed of that event. So it became like an observer-based theory in the beginning, because everything's relative to how something is being acted upon, basically, how these interactions are working. And it turns out there's only one way to do it, and we worked through that mathematics and found out that gives you in our model, it gave us the mathematics of 1 + 1 dimensional spacetime. All full special relativity. Relativity came out of it naturally. It turned out to be the only way that would consistently work to quantify these events in a graph, in a partially ordered set. And that was really mind-blowing, the fact that actually was the only way to do it. And so we published that in the Journal of Mathematical Physics, and I remember when I presented this, I presented that at the APS meeting in Boston, maybe 2009, something around there. 2008, 2009, 2010, that time period. And I was very worried because it was clear to me that because the mathematics worked for this graph, and described space-time for this graph, implied to me that that means that space-time might not actually be physical. It might actually be a description of events, and it might be the unique description of events, the only way you can possibly describe events. But I was not prepared to say that in front of a room of 300 physicists. I didn't feel like getting beaten up. So, excuse me. So I gave my talk, and I just danced around that fact, right? That observation. And I should have known this would have happened, because it's pretty once you go through the mathematics and you see what's actually going on, you realize it's pretty clear that implies that space-time probably doesn't necessarily need to be physical. And I finished the lecture. I went through the proofs and things and finished my lecture, and very pleased with myself. And the first hand goes up, and the first question is, "Wow, this is really interesting. This implies that space-time isn't necessarily physical." Well, shit, I've been found out. Here it is, right on the up. And there's nothing to do but then to just admit it and say, well, yeah, apparently. I mean, this is a it turns out that the mathematics is the unique way of describing these types of interactions. And if that's what's happening in our physical world, then that mathematics describes it. And so we interpret that description as space and time, but there doesn't need to be a space and time. And so right after my talk was a coffee break, and I had 6 people, I counted them, 6 people came up to me several of them actually they thanked me for the talk, very interesting, and they leaned in and whispered in my ear, "I don't believe in space-time either." Like it was a secret. Like there's like the secret cabal of physicists who don't believe. Excuse me. So it's so it's interesting. So fast forward and I'm now studying UAPs, and I very often have people ask me what I think about the possibility of these things being extra dimensional or there being other dimensions. And I tell them, I said, you aren't going to find a supporter here because I don't believe in these dimensions. I don't think these are real. So I don't believe in any, what is a dimension of the question you really should be asking yourself. So my thinking then had changed quite a bit. Um, so as somebody who does foundational physics, I don't think about physics the same way as most physicists anymore. I think that many of the physical laws we see are basically constraint equations that constrain the ways that you assign numbers to quantify things. So I think of mathematics as a technology. I don't think of mathematics having its own Platonic realm it's a technology. We invented it. We invented it to be able to decide which is bigger. Is this bigger than that? Basically, that's what it's for. And that's what we use it for, even in physics. And so you have a set of symbols that are ranked, and then you assign these symbols to objects, and then you manipulate objects. And now the question is, when you combine two things, I have a set here of objects, a bunch of stuff. Here's a set of objects. There we go. And I combine it with some other objects. And so this one I'm going to give it the number 3. I give this the number 1. And I combine the two sets. What number do I assign the combination is the question. And it turns out you can derive that. And this actually was a question I had in graduate school that I was ridiculed for. I had asked one of my professors, I said, I don't understand why it is when I take 3 pens and I combine them with 2 pens, I always get 5 pens. I said, is this an experimentally determined fact that we've just done again and again and believe? Or is it something you can prove mathematically that has to happen? Or is this by definition? And none of my professors even understood the question because they immediately would furrow their brow and like, what do you mean? You're telling me that you don't know why 2 plus 3 equals 5? And I was like, no, that's not what I said at all. I was, why do you add the numbers when you combine sets? And if you look into it in mathematics, that's measure theory, and it's an axiom, which means it's assumed to be true in mathematics. So that's an assumption in mathematics. But it always bothered me. And through my work in deriving probability theory, realized that you can prove it, actually. And so this is where associativity comes in. And the thing is that if you have 3 sets of things, it doesn't matter what way I combine them. The combination always ends up being the same. So the only way to quantify this function, if I have a number here and a number here for these 2 sets, A and B, and then I look at the set union of A union B, what number do I assign to that has got to be a function of the number for set A and the function for the number of set B. But that function has to be associative, and you can prove that it is isomorphic to addition. So any non-invertible transformation of addition will work. So multiplication also works, which is why e to the a times e to the b equals e to the a plus b. That's the transformation there. So addition, the reason you add numbers is actually because of associativity. And so anywhere you have associativity in the universe, you're going to be adding numbers. And so these laws of physics turn out to be, so the addition is basically a constraint equation that tells you how to assign numbers to groups of sets when you perform set unions. So it's a really simple example, but it allows you to see what's going on in a much bigger way. And so I think that a lot of the laws of physics are just rules for manipulating numbers that reflect, symmetries. So these rules are constraining the numbers you assign so that they conform to those symmetries that are holding. And this actually answers Eugene Wigner back in the 1960s, maybe 66, wrote a paper on the unreasonable effectiveness of mathematics, where he was questioning, why does mathematics actually work? Um, and and I think this is why it works, because we've engineered it to work, because we use the laws we have are actually rules for manipulating numbers so that you're doing it consistently.
When you were talking about interactions, it reminded me of something that I'm hearing quite a bit, listening to different ideas in physics about relations or relational quantum mechanics. Is there a connection there?
Yeah, there's some relationship between what we were doing and relational quantum mechanics. They're similar in some ways. I don't, off the top of my head, I don't remember exactly what the relationships are, but they're very similar that way.
So you've mentioned that space-time may not be fundamental, that it may emerge. I'm just curious, where is it emerging from, and what does it mean for something to emerge rather than be a basic ingredient of reality?
Well, in the work we've done, it emerges mathematically. It doesn't emerge physically. So it emerges as a set of mathematical rules that tell you how you need to manipulate numbers when you're considering relationships among different events. So I think this is so that the mathematics of space and time and the special relativistic version actually is what you derive, um, which uh, which is interesting. I mean, it's a little surprising to derive relativity in a whole different way that doesn't involve the constant speed of light. You don't, so it's a little shocking when that happens, and and that really forces you to realize something weird is going on here because we didn't have to use the fact that the speed of light is constant to derive it, which is what Einstein did. You don't have to use that. In fact, you can derive that the speed of light is going to be constant. You can derive that there's going to be a maximum speed such that it's a constant speed for all observers. You can derive that.
Do you think there's some potential for it to perhaps unite general relativity and quantum mechanics?
I think there's a place here, and it might relate to another paper that I wrote, because once we realized that that's what was going on mathematically, um, we found that at the foundation, so when a particle influences another particle, um, and you have an observer measuring what this first particle is doing, when it influences to the left, it the observers quantifying its behavior see the particle as all of a sudden moving to the right at the speed of light. And then when it influences the left, it bounces back and moves to the left at the speed of light. But it turned out that the only speed locally for between events that a particle can go is the speed of light. The only speed that a particle can travel in this theory was the speed of light. And I had remembered that this was actually found from the Dirac equation in the 1930s. And so if you measure the expectation value of the instantaneous velocity of any quantum particle, even a massive one, the only speed it can go is the speed of light. It can't go zero. It's always going the speed of light. And now modern physics, interprets this differently. They talk about the particles scattering off the Higgs field. So the particle bounces back and forth, scattering off a Higgs field. But this theoretical approach, you don't have a Higgs field. It's just the particle's just influencing other things, and it engages in this bouncing back and forth motion at the speed of light. So that was called Zitterbewegung, a nice long German word, which is called Zitter for short, Zitter, means shuddering motion. So when we found this out from our influence theory work, um, it worried me because I thought, well, here we have a massive particle that's going the speed of light, and yeah, that's what the Dirac equation tells you should happen, and the Dirac equation's relativistic, but that doesn't seem to be matching with relativity. So I decided to see what happens. What happens with the velocity addition rule in relativity if you have particle and two observers watching this particle? So observer A is moving at some speed with respect to this particle, and then observer B is moving at some speed with respect to observer A. And then the question is, what is the speed, relative speed between the particle and observer B? And then, so you should be able to get the Einstein velocity addition rule. And so, so I decided to work this out using this idea of zittering. Let's say everybody is zittering. All three of them are bouncing back and forth randomly. The way that you have a zero speed is there's a 50% chance of going left or right at any time step. And that gives you an average speed of zero. If there's slightly more chance of going to the left or right, you're going to have a drift speed. So every macroscopic velocity you see is a drift speed. This cup, well, the particles in this cup are going back and forth at the speed of light, but on average, they're drifting to one. All right, so back to the zitter business. So it turns out that if you have to work this out with the probabilities of particles going left, or observer and particle going left and right. And if you work this all out, it turns out it's a probability theory calculation. So because it's all probability is going left and right. Turns out you can derive the velocity addition rule for relativity. You can actually derive the relativistic velocity addition rule, which I thought this is a whole new derivation of this rule. And it's basically based on stochastic behavior. This is basically a statistical mechanics picture of motion, which is a very different picture of motion. And so then I thought, well, you can then calculate things like entropy because the entropy is based on probabilities. So the maximum entropy state is the one where you're most uncertain about what the particle is going to do. So the maximum entropy state is when it's at rest. At average, it just bounces back and forth, 50% chance of going to the left and 50% chance to the right. That's the maximum entropy state. Now, right, so now you can ask another question. I need a prop here. Well, here we go. So it's a thermodynamics problem. You've got a system in a maximum entropy state. And how do you reduce the entropy of a thermodynamic system? You put in energy. If you put in energy, you'll reduce its entropy, okay? So here we have a ball in the maximum entropy state. It's not moving. What happens when I put in energy? It moves. The probabilities are no longer 50-50. It now has more chance of going this way than it has this way, and the other velocity of that way. So this is a whole different picture of motion. Motion as a statistical mechanical property rather than being mechanics. So I wrote a paper on this, and then it became clear to me. I thought, well, the whole difficulty with relativity, general relativity, is based on rest frames. No such thing as a rest frame because everything's moving the speed of light. Quantum mechanically, there's no rest frame.
Right.
That's why they don't get along.
Interesting.
I think that's the actual root of the problem. That's the first inconsistency I found. So it's actually, whether it's the problem or not, it is a fundamental inconsistency. And I think that's important. But I don't think that's not been recognized yet or anything. And I don't know what to do with it on how to make it better. So we did try to take our work in theory and expand it to do other things and to get to something like relativity, like general relativity. So we've taken steps in that direction. The problem was that our model in influence theory was too linear. It was too much a 1+1 dimensional space. And it's interesting, oh my God. So I actually have to write this up as a publication. I've not actually done this yet, so I'm not going to divulge something that's not published, which you don't typically don't do, right? Um, but why not? So you can use influence theory because the whole theory is based on how you can quantify systems, the of interactions. Um, you can then ask how many dimensions could I use to describe interactions, and so I can do the proof verbally. I can prove this. So say you have n numbers. You're going to use n numbers to describe interactions, and these are your n degrees of freedom. And so ultimately, you'll have n dimensions. Okay. So let's figure out how many dimensions you can use to describe interactions. You have n dimensions. You each one of those numbers is going to be used to construct a dimension, and it has to be linear for associativity and distributivity reasons. So you'll have coefficients on these numbers. You can't treat anyone more special than another. They're all on equal footing. You've got a symmetry there. So they essentially are either going to be plus or minus ones. So the only there's a symmetric way to do it and an anti-symmetric way to do it. So the symmetric way is they all get the same coefficient. So they're all 1 or they're all minus 1. And minus 1 and 1 turns out to be time. So it takes time going forward and time going backward. Doesn't matter which way you define it, it just works. So 1/2 of the assigning 1 or minus 1, 2 ways to do it, gives you one dimension of time, one symmetric dimension. So the spatial ones turn out to be anti-symmetric. So those are ones where half of the numbers would be +1 and the other half are going to be -1, which already restricts you to an even number of dimensions. So 1 + 1 in time and space works. 3 + 1 time and space works because there are 4 total, right? So since you've already got a time dimension, it means that this number of spatial dimensions has to be odd. So you can prove that already. And then the question is, how many ways can you assign plus and minus 1 to your set of n numbers? 10 of them, right? You could do that. But how many ways can you assign pluses and minus 1s? How many ways can you do this? So there are n choose n over 2 is the number of ways to do it. So that's n factorial over n over 2 factorial and times n over 2 factorial. A lot to keep in your head. And of course, if I assign -1 here, +1 here, -1 here, +1 here, I could do it the opposite, and I just change the direction. So it's actually half of that. So it's half of n choose n over 2. And those have to be equal to the number of spatial dimensions, which is going to be n minus 1, because I've already taken one time out. So the equation you have is 1/2 n choose n over 2 equals n minus 1. That's the equation you have. And there's only 2 solutions. One is 1 + 1. N is either 2 or 4. That's it. So you can either have 1 + 1 dimensional spacetime or 3 + 1 dimensional spacetime, which is the answer we all use. That's the more rich version. Both will work. The 3 + 1 works better because it can describe more. So there it is. There you have a derivation of why there are 3 dimensions, which nobody's ever explained this, right? I mean, but you can explain it this way, which is interesting. So it gives you so we had a lot of confidence in this theory. We could also derive things like the action, which is a quantity that you minimize to get, derive things like Lagrangians and all this physics stuff. The action just turns out to be the number of events. It's counting. It just turns out all you're doing is counting, and it gives you all this rich physics, which is really amazing. So we really thought we were onto something. This is it. This is the theory. And then it kind of falls apart. And I don't quite know why yet. It turns out that all the papers we'd published were basically 1 + 1 dimensional versions. We tried to work it out in 3 + 1, and it doesn't quite work. So it's strange because we can derive from the theory that both 1 plus 1 and 3 plus 1 should work, but 3 plus 1 doesn't quite work. I don't know why. And so basically I put the project on hold and decided that since that theory was developed based on by quantifying events based on symmetries, so that you conform to these symmetries, thought let's just focus on the symmetries and see what we can do. So the most recent papers I've been writing have been with my colleague John Skilling, and we've been working on symmetries, using symmetries to derive quantum mechanics in the Dirac equation, taking the work that we did with Philip Goyal early on a good bit further.
Well, I know that your work with UAPs has been keeping you busy, but I'm glad you're still dipping your toes into that side of the work that you do. So I'm excited to see where that goes. So moving on to UAPs, I wanted to know what it was that initially got you interested in taking a scientific look at them. Was there a case, a story, something that stuck out to you?
Yeah, well, I'd always been interested in them. As a kid, I was 10 when Star Wars came out in 1977. So now you can, well, actually, I was 12. I was 12, and in 1977. So Star Wars was May 26, 1977. And then this is from the guy who can't remember anything. You can tell what's important. You can tell what's important. Uh, and and of course, Close Encounters came out that Christmas, right? That was the other studio's response to Star Wars. So the Star Trek movie came 2 years later or something. So but at that time, at night would play the TV show In Search Of. So Leonard Nimoy would host In Search Of, and they very often had UFO stories. So I grew up listening to that. That was on TV usually after dinner, and that's what we would watch. So I was familiar with stories, and I found it interesting. And when I went to graduate school, I grew up in Wisconsin, and I moved to Montana to go to graduate school. I went to Montana State University in Bozeman, and it was about our second week there. So this would have been early September, 1988. There was a cattle mutilation on one of the ranches, where 2 cows were killed, and both were surgically manipulated. One of them, I think, if I remember right, it had like a cylindrical hole punched through it, like a core sample of a cow. I don't know. It was really weird, and there were UFO sightings that night. That night, the sheriff had hundreds of calls and so the local news was all hot and bothered. They were quite upset. And it was, for them, it was either aliens or Satanists, and they didn't know which, and they were very worried about both. And so this became kind of the discussion at the physics department in the hallway especially with the new students, because we've all just moved there, only been living there a week or two, and this happens. And all you can think of is, what kind of crazy place did I just move to? I'm going to have to live here for the next 5 years. This place is nuts. And this is what the discussion basically was. And yeah, we were very loud in the hallway, very excitedly discussing this. I remember at one point shouting, I don't know why aliens would do it or how Satanists would do it. I mean, it was not a high level discussion. It was just a lot of panic and weirdness, right? And one of the physics professors came out of his office and to find out what we were talking about. And I don't know if he was trying to console us. I mean, he was entirely opposite the effect. He said, yeah, well, this happens here sometimes, and they'll investigate it and not figure anything out, and then we'll all just forget about it until it happens the next time. And we're just like, what? Are you kidding me? And then he says, but what's really strange? He says, I have friends who work, this is all present tense, right? 1988. I have friends who work up at Malmstrom Air Force Base, and they have problems up there with UFOs flying over our nuclear weapon sites and shutting down the missiles. We heard about that 30 years ago, right? More than 30 years ago now. And so, and and we look, it was a joke. It turned into a big joke that semester, because anytime anybody would say this weird thing happened, somebody would always lean in, no, it's really weird. They got UFOs shutting down nuclear missiles on northern Montana, and we all would laugh, right? It's just silly. Because how is that possible that if anybody's tampering with nuclear missiles, the Air Force would be all over it, was our thinking, right? So clearly this is nonsense. So now fast forward to around 2015. This is before the New York Times article in 2017. And I was teaching an astronomy course, and we were going to talk about astrobiology, and some of the students had asked me if I could discuss UFOs or any possibility of aliens coming here. And I thought, well, I can talk about the Fermi paradox and the Drake equation, the standard, boring physics stuff that doesn't actually address the problem. And it doesn't actually address the question. Then I thought, well, is there anything else I could say that's intelligent? So in desperation, it was maybe 1 a.m. I start poking around on the internet just to see what could one say about this. And I stumbled on Robert Hastings' press conferences from 2010, where he talked about, he had several, I think maybe 6 people in this panel who had worked at Air Force bases and had dealt with UFOs shutting down nuclear missiles. And the first person to talk was Robert Salas, who was at Malmstrom Air Force Base, the same Air Force Base, talking about events from 1966. And I was just dumbfounded. I was like, I heard about this when I was in grad school. And I thought, but this is real? I thought, wait a minute, this is really bizarre. And then I realized that Salas is talking about events in 1966. I heard about it in 1988, present tense, going on, an ongoing problem. I thought, if everybody just thinks this is silly and it's not, we're in trouble. we potentially have a real problem on our hands. And it worried me. And I thought, somebody ought to at least look into this and see how reasonable this is. So I just started paying attention started trying to read about the topic and educate myself to some degree. And it was only 2 years later that the paper from Helene Cooper, Ralph Blumenthal, and Leslie Kean came out in the New York Times. Was December 17th, 2017, and talked about how there was the ATIP program where the U.S. government had spent something like $12 million to study UFOs. And I was like, yeah, this is actually real. And nobody believes it, and we're going to get blindsided by something if we're not careful. And I thought, scientists really ought to be studying this. And when that paper came out, I thought, well, why don't you study it? I'd gotten tenure, recently, and thought, I'm busy. I got other stuff to do. I'm doing work on exoplanets, but why not try to study it, see what I can actually do? So the first thing I could think of doing was to look at some high profile cases which were rather with dependable witnesses and estimate speeds and accelerations. Now, let's see, how anomalous are these things? How fast do they go? And we found that, for the Nimitz case, the 2004 Nimitz case, where Kevin Day was tracking the Tic Tacs on radar from the USS Princeton, they were dropping from 28,000 feet to sea level in 0.78 seconds. And you can estimate the acceleration as something like 5,700 Gs, which is unthinkable, right? The top speed is about 40,000 miles an hour at the midpoint, right? Yeah, you're dropping from 28,000 feet, which is 5 miles, to sea level that fast, like just as I'm moving my hand, right? That's crazy. And it's easy to say, well, maybe the radar wasn't working, but he used the radar to direct the pilots to the locations to take the videos. So the radar is working. It's not that simple. So, and then it didn't take much more research to find out that Hermann Oberth, who was the mentor to Wernher von Braun, um, he had given a talk on UFOs in, what was it, 1951? Or was it 54? Now I'm forgetting. It was in the early 1950s, I think 54. He gave a talk on UFOs. And in the talk, he mentions that he had seen over 50 radar recordings of UFOs where the speeds were on the order of 19 kilometers a second, about 40,000 miles an hour, which is the speed we calculated.
Mhm.
And why do these people all think that they're spacecraft? Well, it's simple. They move as fast as spacecraft go. The New Horizons probe that flew past Pluto in 2015 is going about 40,000 miles an hour. And it doesn't take much to calculate these accelerations. Once you know what the accelerations are, if you even accelerating 1,000 Gs, 1/5 the acceleration of the Tic Tac case, you can get at 1,000 G acceleration, you can get to 90% the speed of light in 17 hours. So if they could sustain that acceleration into space, this wouldn't just be an interstellar craft. This would be an excellent interstellar craft. And we actually put that in the paper. We put those plots in and showed that you can get out 40, because of time dilation, you can get 40 light year trip. It's a day trip for the traveler. So the TRAPPIST-1 star system, which has several planets in the habitable zone, is less than a day travel away for some of these craft. You could get across the galaxy in 3 months. Now, of course, for everybody in the galaxy, that's going to take 80,000 years, right? But for the traveler, it's 3 months. It's shorter. Those craft could get across the galaxy in less time than it takes us to get to Mars. That's how good these craft would be. And that's the data that we have. So when we actually presented some of this to Aero, and that paper was published, so when Aero had published their statement saying that there's no evidence that these things are non-human craft, it's entirely false. We have evidence of that. And the evidence has been around since the 1950s. They've known this since the 50s.
A large portion of reported UAP encounters, just from doing some research, seem to involve nuclear sites, like you mentioned. And I also noticed a connection between health effects that people reported after, which almost just remind me of radiation, almost a connection there. I was wondering if you have any thoughts on that.
Yeah, there's some evidence that there's radiation associated with some of these objects. I wouldn't recommend getting too close. There's when we went to Catalina for our UAPx mission, we brought radiation detectors with us for that reason, and so radiation's a concern. The other problem is luminosity. These things are really bright. And that has been, Jacques Vallée has written a couple papers on this, not published in academic journals because you couldn't do that back then, but their estimates for luminosities are on the order of hundreds of megawatts of power, hundreds of megawatts of light. And so actually in the special issue in Progress in Aerospace Sciences that, our group published our UAPx paper on the Catalina mission there this summer, first authored by Matthew Shadagas, and I published a review paper on the scientific study of UAPs, the new science of UAPs studies, basically. And those were both published in that same issue, but Jacques Vallée has a paper where they look at a landing. He wrote it with Luc Dini and Mistershi, and it was on a landing where the object landed in southern Mississippi, northern Louisiana, in a clear forest clearing and scorched the trees. The light was so bright it scorched the trees. Actually seen by a physicist. The light was seen by a physicist driving his family on the highway, and realized that that's incredibly bright. And as he got closer, he noticed that the light from the object was washing out the headlights on the street from his car. And knowing the power of his headlights, he did a quick calculation, with inverse squared distances, and thought, that's like hundreds of megawatts of light. I'm not bringing my family anywhere near that. And he literally turned around on the road and drove the other way to get out of there, and then reported it. But they actually went and collected samples of the tree bark, the scorched tree bark, and had worked to study how much scorching was done and how much energy it takes to do that. And yeah, it's hundreds of megawatts of light. So, which is shocking. I mean, I don't know why would you need 100 megawatts of light? And if it's a byproduct of your propulsion system, which has been suggested, then if that's your byproduct, how much energy are you dealing with in this craft? And yeah, it's a phenomenon.
Those are good questions. One thing I noticed too is that a lot of the sightings tend to involve water, either in the ocean, lakes. Do you have any idea why that might be, what that might tell us? And because you have such great knowledge about exoplanets, if that is helpful knowledge, knowing what might be available extraterrestrially?
Certainly. First, I mean, oceans are very stable places. Atmospheres are horrible. We live on the surface with an atmosphere, and it's horrible. The weather changes daily. The temperature changes daily. The temperature changes during the day, right? It's very dramatic shifts in temperature. Fortunately, the swings daily and yearly aren't that huge on Earth, so that's, we can live here. But if you go to Venus, say, you're looking at an atmosphere that's mostly carbon dioxide, and it's 100 times the atmospheric pressure of Earth, which would crush you. And you're looking at, so one atmosphere is like going down 32 feet in water or something. So it's 100 times more than that. That's like diving 3,200 feet down it's like going to the bottom of the ocean without a pressure suit, right? It's gonna hurt. So you can't walk around on Venus. And then the temperature is high. The temperature is like 800 degrees Fahrenheit. And in fact, when I worked at NASA Ames is when we had the Magellan probe in orbit around Venus and was recording, doing radar mapping. And they had a really interesting mystery happen that they found the mountaintops would become radar reflective at times. And they noticed that this was correlated with the drop in temperature. So it would cool down to maybe 600 degrees on the mountaintops. And then you'd get this radar reflectivity. And they found that what it was is you had lead and bismuth gas was actually snowing out of the atmosphere. You would get lead and bismuth snowflakes collecting on the. I want to see what that looks like. I can't imagine what metal snow would look like. But we joked that that's a cold day in hell. That's literally a cold day in hell. That's what it's actually like. So that's Venus. That's another atmosphere, right? And now you can go to Mars. Mars is 1/100th the atmospheric pressure of Earth, so you need a pressure suit, and it's about 100 degrees below 0 Fahrenheit. It's very cold. So atmospheres are tough places to be. The temperature can vary by huge factors. The pressure varies by a factor of several thousand. Yeah, so the temperature varies dramatically, the pressure varies dramatically. But now consider an ocean. If you're in an ocean, you're in liquid water. So if you consider a water ocean, you've got a liquid water ocean. The temperature is going to be between 0 and 212 degrees, right? Or 0 centigrade or 32 Fahrenheit and 212, or 0 centigrade and 100 centigrade. So you're constrained that the temperature is within a narrow range, and it's going to always be there. I learned how to scuba dive when I was in grad school, and I did my training in Lake Superior. It's a cold lake. In August even. At 60 feet, we did a wreck dive, which was amazing, like a big iron ore freighter that just got torn apart by bashing into this cliff in one of the notorious storms. It was terrifying. Um, but at depth, at 60 feet down, it was 32 degrees was the temperature of the water. And I remember telling our dive instructor, I said, I don't believe it was 32 degrees down there. He goes, and that's good because now you know you can dive in water anywhere because it will never be less than 32 degrees unless you're in salt water, then it can be a little less. Yeah, so water's got a set temperature range. The pressure varies by depth, so you can go down to the depth that you're comfortable at, and the only thing you would really have to worry about are chemical contaminants in the water, minerals that are poisonous to you, perhaps, or biologics, right? Bacteria and such like that, or shark. Those are your big worries. And so on any planet, and that's an interesting thing. So oceans are great places to go. And if you're going to be traveling from star system to star system and you want to be prepared for hanging out on a planet, you either should be prepared to hang out on an airless world because there's going to be lots of those, or you should be prepared to hang out in an ocean because oceans are apparently rather common. They're rather common in our solar system. We believe that they're probably common everywhere. So Earth is a water world. It's the most poorly named planet in our solar system next to Uranus. Um, and then but Jupiter has several moons. Europa, Ganymede, and Callisto all have subsurface oceans under ice, and Saturn's moon Enceladus has liquid water under its ice as well. So there are lots of places you could go if you're a water dwelling creature. Plus, you can hide. I mean, it's a great place to hide. Electromagnetic waves don't travel well underwater, which is why we use sonar, and so you can hide. You're protected from ultraviolet radiation from the star. You're protected from cosmic rays. You're protected from small meteorites, at least. So there's a lot of protection there as well. A lot of reasons to go to the ocean.
So when you are studying an anomalous case or looking at UAPs, what kind of evidence are you looking for or would like to see to determine whether there's some scientific validity there or not?
Yeah, that's hard because it's not evidence that people can normally collect. Normally people take photographs, and photographs are tough. It's usually a photograph of a light in the sky, and I get these sent to me all the time. What can you tell me about this photograph? I said, well, it's a light in the sky. Looks like a light in the sky. What the light's attached to, I can't begin to tell you. And that's really the problem. And so what do? You can't do much with that. And even especially with cell phones, I know skeptics will complain. With all the cell phones, you expect more pictures. Cell phones are made to take selfies. Those cameras are not. If you're a photographer, professional photographers know, I do wildlife photography. I don't use my cell phone to do wildlife photography. I know better. I have a real camera. I have a real camera, 400 millimeter lens, Canon, a nice Canon camera. And most people aren't carrying one of those. And the cell phones, I was actually trying to get a photo was flying back from Austin last week and was flying over the clouds, and the sunlight was reflecting and refracting through the clouds, and I had a beautiful rainbow circle pattern with a shadow of the plane inside of it. And I was trying to get a photo of that with my camera phone through the window of the plane, but because we had gone through the clouds, there were water droplets on the plane, and the camera kept focusing on the window pane and not the object, not the beautiful rainbow I was trying to take a picture of. So I couldn't get a picture of it. So these cameras are not controllable, and you can't get the photographs you want. So it would be good to get good photographs, of course, with professional equipment, and you actually want multiple photographs from different angles, with known distances between them, so that you can perform triangulation. You can then figure out the size of the object. That way you can figure out speeds. You can then calculate things like that, but you can't estimate speeds from one point. That's just not possible.
In your view, what kind of questions should physicists or people interested in this field be looking at in order to move this field forward?
Wow. That I ask myself that all the time. I don't have good answers. We physicists focus mainly, we fixate, let's use that word, on propulsion, because we don't know how these things are off the ground in the first place and how they're moving. They don't seem to interact with their environment. They'll fly through the air, without sonic booms, without sound, without sonic booms, without fireballs. Um, Something going 40,000 miles ought to be on fire, right? And there ought to at least be a sonic boom. And some of these craft, like the Japanese airline JAL 1628 in the 1986, I think it was, there is about 45 minutes of radar observations of this object that followed a 747 for 45 minutes across Alaska. And this object is jumping from one side of the plane to the other. The craft is about 4 747s in length. So it's about the size of an aircraft carrier. It's shaped like a walnut. And it's jumping from one side of the plane to another, 7 kilometers on one side to 7 kilometers on the other side in like 12 seconds. And those accelerations have been estimated. Daniel Kumpe, another physicist from the Niels Bohr Institute, estimated them to be on. Some of those accelerations were about 10,000 Gs. How do you accelerate an aircraft carrier at 10,000 Gs? So that's why we fixate on these problems. And why doesn't it interact with the air? That's very strange. And then the underwater ones are similar. There's a case in New Zealand with a New Zealand frigate that was actually doing experiments, going out from Auckland through the Rocky Gulf out into the Pacific, and then coming back, trying to lure in unknown submerged objects. They'd be followed in at times by objects that they would then try to measure with sonar. And at one point, they were followed by a really large one that was about 150 feet wide and about 800 feet long. And so it's 30% larger than the largest submarine, which would be a Typhoon class submarine, about 600 feet long. So this thing bigger than a submarine and no propeller wash. And it was 2.5 kilometers behind them, and then suddenly closed the distance. Sorry, that's an alarm. It suddenly closed the distance in 25 seconds, covered that 2.5 kilometers and went under their ship. And the speeds underwater are about 3,000 miles an hour. You've got to clear out a 150-foot diameter cylinder of water that's 2.5 kilometers long in like 25 seconds. And I'm not sure I've got all the numbers right, but I know it's 2.5 kilometers. I think it was about 25 seconds. It might have been shorter. And so that's incredible amount of water to move out of the way. So it's a huge amount of energy. Water is not compressible, so you can't squeeze it out of the way. You've got to lift it up. So there ought to be a wave above on the surface. There's no wave to observe. When it went under the ship, it disturbed the ship by only taking out the power. All the power went out, and the batteries were drained. So they were adrift. They were adrift then for about 4 hours before they were rescued. Couldn't even radio for help. And so the underwater one doesn't seem to be interacting with the water, yet you can get sonar measurements from it, which means sonar works by having pressure waves hitting the object and bouncing off. So pressure waves are when the atoms or the molecules are actually banging on the object. So the object is interacting with the water in some way, but not in another way. And so how do you reconcile that? And I don't know how. So it's very strange. So those are some of the questions. Another question is, what happens to the energy when these things stop? So in the Nimitz case, when the Tic Tac drops from 28,000 feet to sea level, it stops dead, right? Well, all that energy from its motion had to go somewhere. Energy just doesn't disappear. And in fact, we estimated if you estimate the mass of the Tic Tac is about 1/10 the mass of the F-18. They're about the same size. So we tried to lowball the mass. So we took the mass of the F-18, dropped it in order of magnitude, and said that's a lower bound about for the Tic Tac mass. It has to at least be that. And if you do that, you get the amount of power that maneuver required was on the order of a terawatt of power. 1,100 gigawatts of power, which is huge. But then all that energy has to go somewhere. It should have been, so we estimated it should have been an explosion equivalent to about 250 Tomahawk cruise missiles going off at once. It's what should have happened when it stopped, but that doesn't happen either. So we don't know what's going on with these. They're not moving the way we think they're moving. So something very different's happening. This isn't regular motion the way we used to thinking about it.
Right. Do you think there's a connection then to what we were talking about with some of your theories or proposals about space time? Do you see those two fitting together at all, or you keep them separate?
No, that's a good question, and I'm not sure. That's something I think about sometimes because that whole theory was based on the things that everything is influencing everything else. But you could have a situation where if you could control what you're influencing, then maybe they could just not be influencing anything else and then just change how they interact. So let's think about it this way. So there's no space and time. These are just events and interactions. That's all you have. So there's no such thing as over there, right? What you mean by over there is something that's over there is interacting with its environment differently than you're interacting with it. So if you changed how you're interacting with something, your position in this whole mass of objects and interactions will change. So if you can control how you influence other things and how you're influenced by other things, then you could simply just change your position by changing how you interact with everything around you.
So, like two observers experiencing a slightly different reality in a way by changing how they interact.
Yeah, well, the reason you're here and not over there is because you're interacting very you have dense interactions with things here and not the things that are over there with different things, right? And so now if I want to be over there, I could stop interacting with these things and start interacting with those things, and then I just would be over there. That's how you would interpret it. So there's a way to think about it that way. I don't know how you could control your interactions, but if that's a good description, if that's a good fundamental description of what's happening, then there are other ways to move, which is an interesting thought.
One more thing I'd like to ask about UAPs is have you noticed a connection between encounters, sightings, and electromagnetic anomalies?
Like, what do you mean anomalies? You mean environmental anomalies or anomalies created by the objects?
Areas where there might be strange readings, GPS is not working properly. I guess I'm thinking as a example, almost everyone should know is Skinwalker Ranch. They seem to be having electromagnetic anomaly there. So I didn't know if there's been if anyone's looked at there being a connection possibly between the two.
Yes, and in fact, yeah, the people at Skinwalker Ranch, Travis Taylor and Eric Bard and others have been looking into this. Um, my colleague Matthew Shadagas has been there, and he actually he had a magnetic field meter with him, and if I remember right, he would remember exactly. But if I remember right, what happened was he didn't have any magnetic field recordings on the ranch at all. Like he couldn't measure the Earth's magnetic field when he was on the ranch. Yeah, there was something really strange about that. Um, yeah, it's not clear what's going on. Yeah, there are electromagnetic anomalies. UAPs often seem to emit very strong electric fields. This is one reason that one explanations for cars being shut down is that they're ionizing the air around them, and gasoline engines then can't run because the spark plugs short out. Won't kill a diesel engine, but it'll kill a gasoline engine. Um, which is what's funny when you watch Close Encounters, because Richard Dreyfuss's character is driving a Ford F-150, and his truck stalls. A Ford F-150 is a diesel engine. That should not have stalled. Oh, here we are, physicists ruining the fun in a movie like that. But yeah. So yeah, so these are interesting. Yeah, so they seem to create really strong electric fields, and so we try to measure electric fields and magnetic fields as well.
Has researching these things like emergent spacetime, information, anomalous phenomena, has it changed the way, I guess, you see reality or see your place within it?
It's the one thing that it's really done is it's made me better appreciate that I don't understand the universe as well as I thought I did when I was taking my physics classes. I mean, the fact that you can derive special relativity from as being the unique way to quantify partially ordered sets of events is a strange thing. And it suggests that we don't quite understand what we're doing yet. It's one thing to get a lot of the mathematics right, but when you don't know why it is the way it is, which is definitely what's going on with quantum mechanics, people admit that freely. Um, you're you're it's important to keep in mind that you should be humble because you're admitting that you don't understand it. There's something you don't understand, and I think that a lot of physicists get very excited about being able to do calculations and forget that that does not mean that they understand it. Um, Very often yeah, as professors, we're often critical of people who make claims like that. So you'll have people say, "Well, I understand the physics. I just can't solve the problem, the homework problem." Well, and we're thinking, well, if you can't solve the homework problem, you don't understand the physics. But the other case is also true. Just because you can solve the homework problem doesn't mean you can understand the physics. And I think we forget we professionals forget that.
Speaking about students, is there anything wish you could tell younger scientists who are curious about questions that maybe fall at the edges of where science is comfortable and might want to look into some of these more weird areas of science? Is there any advice you'd give them?
Yes. First, be curious. I mean, if you're going into science because you're curious in the first place, don't stop being curious. Be curious. Some of these things are weird and not all of it may be true, but from what I've seen looking into some of it, most of these weird phenomena have at least a nugget of truth to them. There is some element of truth there. And ferreting that out and understanding it, I think, is worthwhile. Um, you probably don't want to jump into that early in your career. And if you do, you might do it a little quietly, because not everybody in the profession looks at that favorably. Um, and I think that's it. I mean, stay curious and don't, keep in mind that you don't understand everything. We don't.
It's true. And I always think that if you want to question the basics, the best way to do that is learn the mainstream method first. Understand that in order to question it with just a
And then
little
when
bit of
you see points where the mainstream starts to break, those are the interesting places. I mean,
Mhm.
those are where the big discoveries are actually, right? And it's easy to ignore them and say, "Well, that's too weird. I'm not going to study that." But now you're not studying the thing that we don't know anything about. There's going to be new discoveries there. There's potentially low hanging fruit. It's all there waiting for somebody to just go in and grab it. And and yeah, in some of these cases, these topics are taboo, to some degree, and so you have to tread carefully, but that's all there is to it, and, And relativity wasn't accepted right away. And in fact, there was a talk by, oh, I don't remember but there was a talk, Ludwig Boltzmann gave a talk on entropy in particles and atoms. And basically, in the beginning of statistical mechanics, when this all started in the late 1800s. And one of the other professors, scientists whose name is just escaping me right now. Don't know why. It's my weird associative memory is saying there's an E there somewhere, but I'm forgetting his name just right now. But anyway, so one of the other well-known scientists was at the talk and left his talk flustered. And he said something like, I can believe in atoms far less than I can believe in relativity and something else like that. I mean, it was like he was basically declaring that he didn't believe in relativity, but he believed in atoms even less, right? So it was not a popular thing to study, but look what it did. I mean, look what happened when they knew that there were atoms and then figured out how atoms worked, which gives you quantum mechanics. Actually, this is how we're kind of in this weird mess now where we don't have major discoveries, because what I think happened is you had quantum mechanics was such a big surprise. And once it was figured out, you were able to calculate so many things with it that you couldn't calculate before. You could figure out why this why this is red and that's green. You can figure that out with quantum mechanics. And you can do those calculations. So physics turned into this enterprise of using quantum mechanics to calculate things. And the whole field of solid state physics and condensed matter physics is basically that. Using quantum mechanics to calculate what groups of atoms are going to do. And it's very powerful. It's very useful. And, but it put us in a mindset where all you have to do is take the equation and then calculate something and you've made a discovery. And put us in this mindset where that's how discoveries are made. And along the way, I think we've kind of forgotten that those are how some discoveries are made. The big transformative discoveries are made by considering the weird problems that nobody has a handle on. Those are where that's where the paradigm shifting happens. And those are the huge discoveries. And we haven't had one of those in 100 years. And I think that's because quantum mechanics was such a surprise and so useful. And I think kind of put us at a disadvantage.
Hopefully, in the next decade or two, we will get back on track and make lots of new discoveries.
Every time science has gotten to the point where we pretty much know everything, somebody comes up with a surprise. I mean, there's obvious big discoveries on the horizon. I mean, the whole dark matter, dark energy business is clear. The whole fact that what is the universe shaped like and how did the Big Bang work now that we actually better measurements of the cosmos is also interesting. And those are the obvious ones, but then there are the weirder, mysterious ones that we don't have a handle on. The whole UAP phenomena is full of mysteries, and not all of it's real, but some of it is. So now you have to take the time and sort it out.
I forgot to ask this earlier, real quick, about what proportion of sightings or reported cases have been determined to be truly anomalous, ones that we're still trying to determine what may have happened.
I think the estimates are that about 4%, 3 to 4% of sightings are interesting.
Well, thank you so much for sharing all your information with us today and joining us. I hope to see you again so we can discuss some more ideas and possibly some additional publications.
Right. Thank you so much for having me. I really appreciate it.